All right, so last time we were talking about what if we were building computers from scratch? What if we didn't have transistors? So we talked about vacuum tubes last time, right? What's a vacuum tube?
Big cylinder that has an electrical circuit,
Okay, what does it help us represent?
numbers, or on or off.
On or off, zeros and ones. Helps us. So this was back in the day when we didn't have transistors, so we had to turn a bulb on or turn a bulb off, and that represented a binary digit of 0 or 1. So then we asked the question, what if we were representing Java's size of int? So we had 32 bits, so we needed to do math with 32-bit numbers. Mr. Quiz,
Really?
I'll let you do it real quick.
All right, what's the question?
Right there. You have to do it while I'm talking. Well, why is it that you just don't leave earlier?
No, I should leave.
Like 5, I mean, well, just 5 minutes. He's lucky I like him.
If it was me, no.
No, seriously not. I don't get pretty little squiggly made up languages on the top of all my papers from you.
This is the first quiz I think I've got right in a while.
That's good. So that means you went home and studied this?
Yeah.
So you did?
And we actually talked about it at 490 yesterday too.
That's because Dr. Locklear and I and Professor Wall got together. We were talking about how idiocy was creeping its way into our computer science department. As seniors, you should not know how to convert binary numbers to decimal and vice versa. That's just an absolute embarrassment if you can't do that.
Still got half a year.
I would probably make the argument if you can't do it as sophomores. But certainly as seniors.
I can do it. I can graduate.
It's one of the requirements. Like, I bet you I could walk into a McDonald's and find at least one employee at that McDonald's that could answer this quiz.
I don't know which McDonald's.
No, I think any McDonald's. I would be surprised if I couldn't find one person in there. Which means you're not fit for McDonald's. Free food, though.
The food.
At least you do have that going for you. You do have that going for you.
So I'm tempted to, like, I don't know, maybe work at like a Toppers or a Pizza Hut, or a sub place. Every time you want to go home, just take the bread.
I get it. It's opportunistic survival instincts.
No.
You're going to need those given your computer science skills. But I am impressed, Skippy, that you were able to come in today and fill out this quiz. So that does show a level of effort on your part. Because clearly just because you did something in a class doesn't mean you know how to do it. Because I think at a minimum you've seen how to convert binary numbers to decimal and vice versa in at least 4 classes. Minimum of 4 classes. I'd be surprised if you didn't see any more than that. And in 250 you wrote a program to do it generically both directions. Tennis players. All right, so that's why you covered it. Your 490 class. There was we had a discussion. Did you get it right?
Yep.
Yep. What's with all my leading zeros here? Did you solve this the same way Skippy did?
I think so.
You just figured out what's the biggest number that's not too big for it? Yeah, see, the mathematical way, you just keep dividing by 2, recording the remainders. Yeah, so 487 divided by 2 is 243 as an integer. 243 times 2 is 486, remainder 1.
But then you have to read it down.
And then you read it from bottom up is your final answer. So you keep going until you hit a 0. That's the. I mean, there's nothing wrong with the way you did it. I mean, just I was saying to Skippy, if you were doing this for as the number gets larger, 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 this becomes more tedious. Where this is a consistent, you just keep doing the exact same math. Divide by 2, record the whole number quotient, record the remainder over and over and over again until you finally get a 0 here. Then you're done. But your answer is correct, so I'll take it. We had a relatively heated discussion about that at Bible study yesterday about the inability of
Seniors?
not all seniors.
No, not all seniors.
Like you knew how to do this, right? Before I yelled at you on Monday. Huh? And I'm okay with that. So I've shown you a more mathematically sound way of doing it, but the point is you could do it. Did you know how to do this before Monday?
You learned it in 150.
You definitely learned it in 150. Probably saw it again in 175. Definitely saw it in
I would take
250.
175.
You definitely saw it in 250. And I don't care about the other people.
That's actually working. Computer in my house.
See, I don't even care about the other people. I just know you saw it from me. So we have some competent computer science majors, is what I'm saying.
Working on it.
All right, so if we had a 32-bit, if we were building a computer with vacuum tubes, we wanted to represent the math size of the number size for integer mathematics for Java. Now we have 32 bits that we need to represent. So 32-bit integers. To support that for signed integers, we're going to need 32 vacuum tubes, right? Per int. So if you want to be able to add two numbers together, you're going to need 64. That makes sense? Now, in Java, we're trying to make this equivalent to Java. In Java, if you take two integers, let's say in Java we took 1.8 billion plus 1.8 billion. What would we get? What would the result be? So if I had this line, int a is equal to, it's 100, 1800, 18,000, 180,000. Is that 1.8 million? That plus that. What would a be equal to after that? So if I did system.out.println a, what would I get? Why would it be too big? My magic, I utilize the stars. It's a thing. It's time. There's a propagation delay. So this is 600. This is 3.6 million. No problem, right? What about 1.8 billion? So that's 18 million. That's 1.8 million, right? Or 1.8 billion. All right. 1, 2, 3, 4, 5, 6. Is that 3.6 billion? Is that what that number is?
only doing 180 million.
Yeah, but I'm adding them together. Well, but
It'd only be 160 million.
I want this to be billion. I want this to be 1.8 billion. Is that what this is?
No, it's 180 million.
Well, that's 180,000.
What's another 100?
That's 1.8 million. That's 18 million. Shouldn't that be 1.8 billion?
No, it's 180 million.
You need one more zero.
Just one more.
There?
Oh, shoot.
All right, good. Well, that's the answer I was, well, that's like the answer I was expecting. I didn't have like the exact answer in my mind. That's roughly the answer I was expecting. So we got a negative number. Why?
Kids are only, what, 32-bit signed numbers?
32-bit signed numbers. What's the largest value we can store inside of an int? Positive 2 billion, right? So an int is plus or minus 2 billion is the range of values you can store it at. So I took 1.8 billion plus 1.8 billion, which should give me 3.6 billion, which is too big to fit into an int. So what happened? It ended up wrapping back around. Well, how does that work? Let's say to do this in a simpler example, let's do with bytes. If the largest byte is since bytes are signed, I'm just going to use 7 bits here. Okay? So that's the largest byte. That is a positive 128. What if I add 1 to that? Well, 1 plus 1 is what? 2 with remainder 1, so that'll be a 0. Then another 0, because this would be 1 plus 1 is 2, remainder 0. Another 0.
It's gonna be a bunch of zeros.
Another 0. Another 0. Another 0. Maybe we have so far 6. Another 0. Like that. And then we have 1 extra carry bit. Correct? Because I didn't mean to make that funny, but now I get how it's funny. You just looked at it. That's kind of funny. So the positive representation of this number, I would have used that very first bit for the sign bit. So a 1 would mean it's positive. That makes sense? A 0 would mean it's negative. So this is actually the positive number. Well, I'm actually kind of still not doing that right. Let's say that's the positive number 1, just to fake this for a second. So when I get all the way to the end here, I'm going to have one more 1. 1 plus 1 is 2, which is a 0 with a 1 carry, correct? So there's my 0. But now I have a bit sitting over here, but nowhere to put it. That's called an overflow bit. So that's why it's circled back around. This is what number? When I had that overflow bit, what ends up happening is all these guys turn into 1s. So now I have negative 127 because I had an overflow bit. That's why it wrapped. That's why it went negative. So if I were to add, just to kind of show you this in practice, if I said byte B, if we're making funny jokes, if I say byte me is equal to 127, and then I printed out me, and then I printed out, then I said me plus plus, and printed out me again, and then I said me plus plus and printed out me a third time, I should print out a 127, then I should print out a 128, then I should print out a negative 127.
So if it
Actually, no, hold on, I'm lying. It's negative 128 to positive 127. I should print out a 127, then a negative 128, then a negative 127. So that's how we see it wrap. So 127 plus 1 in 8-bit math is negative 128.
Basically, if you go over on the positive end, you're going to the negative.
Right. And we just showed why that happens. Because we use that first bit for the sign bit. And then we can get an overflow where we don't have any place to store the extra 1. And the overflow means wipe the other guy clean. Flip all the bits. It's like a not in Boolean. That makes sense? How that guy works? Okay. So, just more interesting computer science, trivia type stuff.
When you said flip all the other bits, if it was a 1, it would become a 0, right? Not
If what was a 1?
if you had a 1 in there, for example.
So let's say the number looked like this and we had a carry bit. Yeah, that would circle back around. So these would all become zeros. And to illustrate going that direction, if I start this guy off at negative 127, printed it out, then subtracted 1, printed it out, that would be negative 128. Subtracted 1, this should go to positive 127. Make sense? So it goes both directions. But it wraps because of those carry bits, not just because there's some if statement in there that says, okay, well, if you're too big on the negative side, just make yourself the biggest positive number. That's not why it works. It's how binary math works. So the punchline with that is, getting back to this guy, is we can only represent numbers with 32 bits in here. So if we wanted to represent 32-bit integers and be able to do 32-bit math, the biggest number at any point in time that we can represent is, especially if we're going to support signed numbers, the biggest number that we can represent is positive 2 billion and some change. Okay, so that's a positive 2 to the 31st power minus 1. That's the largest number we can represent on the positive side. Because I need to use one of those 32 bits to keep track of positive or negative. Make sense? And just for future reference, I only kind of showed you a halvesy example here because actually subtraction uses something called 2's complement. Not that important we go into that, but just understand that it wraps because of the way binary math works. Okay. Get rid of that. So we'd have 32 vacuum tubes per int. So let's call that a total of 64 vacuum tubes for math. Well, to hold two numbers. To hold your number 1 and the number 2. Then your answer can go back into number 1. So you can accumulate into num1. So you really only need 2 different 32-bit banks of vacuum tubes in order to hold our numbers. Now, we also are going to need, for math, 1 carry bit. See, it's less funny now when you see how it's spelled. So, 1 carry vacuum tube. It's the reality here. Okay. Now, what about the math units? Well, we saw how to do addition. Let's just assume that all of them are similar. So, how will we implement addition? Well, we had our slide here. This was num1. This was num2. We needed to store our running total somewhere, right? So we need a third bank of vacuum tubes. addition requires another 32 vacuum tubes just for data representation. Okay, just for data representation. But now we need to actually solve the problem of addition. Well, how do we solve that problem of addition? Let's do it on another slide. So this is called, let's say this is called bitwise addition. Bitwise addition has some rules. 1 plus 1 is equal to 0, remainder 1. Or we could say 0 carry a 1. Okay, 1 plus 0 is equal to 1, remainder 0. 0 plus 1 is equal to 1, remainder 0. 0 plus 0 is equal to 0, remainder 0. That make sense? How would you implement this? If all you had to work with was vacuum tubes. What we're trying to understand is why these computers were the size of gymnasiums, or at least the size of large rooms. So I'm looking at a wall. And what do I see on that wall? I see 32 vacuum tubes. Right underneath it, I see another 32 vacuum tubes. Some lights are on, some lights are off. Then I see probably another, I see a couple of like, plus sign, a minus sign, a divide sign, and a multiplication sign, painted on there with a vacuum tube next to each one. So I turn on the vacuum tube with the math I want to do, right? So now the computational function, the demon inside the machine has to go and actually do the math function. How would you do the math function? If you had 64 vacuum tubes, 32 for number 1, 32 for number 2, and I told you to add those together, but you had to give me the recipe, the mechanical recipe for adding those together, what would you do? Keep in mind we don't have software. So we're back to that question of when do we need an operating system? When don't we need an operating system? Can you give me a recipe that will work on any 32-bit number added to another 32-bit number that will always, 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 always work? But we have to implement it mechanically. Not in software. Give you a hint. Let's see where our numbers. These guys. So these are. I need 24. So if I'm adding these two 32-bit numbers together, here's my 32 bits that represent the first number. And this first number is what? Well, this is the ones place, the twos place, the fours place, the eights, the 16s, the 32s, the 64s, the 128. This is 128 plus 64, blah, blah, blah. This is 256. Okay? And this is the number what? 1.
Like I couldn't see it. Your cursor was in the middle of it all.
So if I'm adding these together, 1 plus 1, so I'm going to take this bit of this guy and add it to this bit of this guy, and I'm going to get a what? A 0 as an answer with a carry bit. So we started off with a carry of 0. So what happened here? We took 0 plus 1 and got a 2. A 2 is a 0. So 1 plus 1 is a 0, remainder 1. So there's our 0, and here's our remainder. Then we move to this guy. 1 plus 0 plus 1 is 2. 0, remainder 1, so on and so forth, right? So that's your hint. So the reality is that it's not just 1 plus 1. It's carry plus 1 is, well, actually, let me ask you this. Can you give me an example of a number that when added together would give us a 3? One plus 1 is what? That's a 2. So we would put in a 0, remainder 1. 1 plus 1 is a what? That's a 3. What's a 3?
So 1 remainder 1.
1 remainder 1. That's what it is. 1 times 2 is 2, remainder 1, to give us a 3. That make sense? All right, so we need to fill this out a little bit more. So we have 3 things. Now, so we have a 1 plus 1, which is a 1 remainder 1. We have a 0 plus 1, which is a 0 remainder 1. We have a 1 plus 0, which is a 1 remainder 0. We have a 0 plus 0, which is a 1 remainder 0. We have a 1 plus 0 plus 1, which is a 1 remainder 0. We have a 0 plus 1 I'm sorry, a 0 plus 0 plus 1, which is a 1 remainder 0. Hold on, I screwed this up already. Okay, this 3 is a 1 remainder 1. A 2 is a 0 remainder 1. A 2 is a 0 remainder 1. A 1 is a 1 remainder 0. A 2 is a 0 remainder 0, remainder 1. A 1 is a 1 remainder 0, like that. Then we have a 1 plus 0, which is a 1 remainder 0. Then we have a 0 plus 0, which is a 0 remainder 0. Zero remainder 1. There we go. That make sense? So for bitwise addition, where we have 2 bits and a carry bit, we have 8 different permutations. It's 2 to the 3rd power. Make sense? So we need to build each one of these. So getting back to this, if you were to give me an algorithm for adding these two numbers together that works every single time, a mechanical algorithm, what would you say? We always do these numbers from right to left, correct?
Yep.
For binary. So let's just call this guy here, this far right one, bucket 0, then bucket 1, then bucket 2, then bucket 3, then bucket 4. So let's think about them backwards, like reverse strings. Okay? So would you say that it is, let's say this is N1, and this is N2. And that's our answer. So would you say we need to say N1 at bucket 0 plus N2 at bucket 0 plus our carry bit equal answer at bucket 0. Isn't that the way the math should work? So that will give us what we should put in answer at bucket 0. It should also give us what the new carry bit is. Update C. N1 at bucket 1, N2 at bucket 1, plus whatever C is, will produce for us answer at bucket 1, then update C. Do this 32 times. If you do that 32 times, are you guaranteed to always do correct math for 32 numbers, or for 32-bit numbers?
Unless you went over, but
Well, we'd have one final carry bit,
okay.
right? I understand what you're saying. We're not dealing with that final carry bit at this point, but we have it.
Okay.
Okay, we have that carry bit. So at the very least, we can do math with 32-bit numbers. But what are we doing? We're being kind of inefficient because we are literally dealing with all 32 bits every single time we do math. Does that make sense? We don't have a choice in this case. Our approach to doing math in these old computers is a brute force approach. Like you could hold 32-bit numbers, fine. If you want to add the number 1, no biggie. That is 31 zeros followed by a 1. Actually, for a positive 1, it would be 30 zeros with a 1 in the front for a positive number. So you'd have the number 1 would be represented as 30 zeros followed by a 1 with a 1 on the far left bit letting you know it's positive. So that this guy's not used for any math, it's used just to represent positive or negative. That make sense? So if you did have a carry, you would flip that bit and then flip all the other bits. And that gets you the wraparound. And 2's complement is a more efficient way of doing that. So these guys, maybe the earliest machines didn't do it. They just did it literally brute force. But, you know, whatever. You were getting the picture that we're dealing with a wall of vacuum tubes, right? So not only do we have a wall of vacuum tubes for representing our first number, and another one for representing our second number, and another one for representing our answer, and then a single vacuum tube for representing our carry bit, and then probably 4 vacuum tubes to represent which math we're doing. Add, subtract, multiply, divide. Now we also need to represent all of these.
Too many tubes.
Well, how would you program? I use that term know, the biblical sense, I guess. How would you program or build the circuit, the vacuum tube based circuit, to do this math? You would literally, how many vacuum tubes does it take to represent all of these? This is our carry bit. This is our bit from num1. This is a bit from num2. Right? Okay, so we're going to run some wires off those guys. So these are given information. Now we have a wire that's going to run from this guy into answer at bucket 0. That make sense? And we're going to have a wire that runs from this guy into our carry. So we're going to need 8 of these. Each of these 8 are going to be hooked up to 32 different buckets. Now the reality is, in the early days, because you have, electricity interfering with other electricity, they probably represented them as individual. They probably took all these things, these 8 different mathematical functions, and reproduced them 32 times, 31 times for all the bits. That make sense? So we had one of these guys. This is probably going to be a wall of. So we'll have a minimum of 8. How will we represent that? So we'd hook this bit up to num1's current bit, this bit up to num2. This bit's the carry bit, num1's current bit, num2's current bit. We'd actually probably, for interference, we'd probably copy the carry bit 32 times. So we'd have this hooked up to its own copy of the carry bit. That way you didn't have electricity over, screwing up our answers. So you'd have one wire coming out of each of these, pointing to one bit in each of our numbers. Coming out the other side, we'd have this guy wired to the equivalent vacuum tube on our answer row, answer row of vacuum tubes, and this guy wired to the next carry bit on our 32 bits of carry bits. So to do it that way, we're actually going to need 32. Let's say 31. Well, no, 32. We'll keep that last one. 32 carry vacuum tubes to store all of our carry bits. That make sense? So the representation of that is we'd actually have something that looks like that for our carry bits. And then every single time we had a carry bit, we'd throw the 1 up there, that kind of stuff. So this carry bit is related to this bit from num1 and this bit from num2. That makes sense? So we're starting to get an idea here. A wall of vacuum tubes hooked to another wall of vacuum tubes just for doing addition. All right, let's tackle subtraction. Now let's tackle multiplication. Let's tackle division. So for a primitive calculator, that's a dorm room, right?
Crazy.
And do you think that those computers only did math, add, subtract, multiply, divide? Chances are, if they were building computers, it was more than just to do 2 things with 2 numbers. They were probably having the ability to take in a bunch of information. So now you have to be able to feed information to it in some way. That's where things like magnetic tape came in. Remember the pictures we looked at last class? It almost looked like it was a film projector. Remember those? It had a film, and that was probably feeding the input and also capturing the output. Because at this point, what's the output? Well, the output's what the human has to, after this thing's done clicking and crap, and all these Christmas lights lit up under the answer, then the human being can walk up and say, there's our solution. We just added 37 plus 58. We have our answer. So those were our early computers without software. Make sense? All right, we'll pick up there on Monday. If you're traveling, have a safe trip. Blah, blah, blah. Don't overeat. Or if you overeat, do it right. All right.